All right, if you could please type here in the chat to let me know that you're present. So today we are going to continue talking about transient analysis. We're going to kick things off today by looking at an RC circuit. So let's look at the following circuit where we have a voltage source Vs that is connected to a network containing a resistor R that is connected to a capacitor C. In this network, our switch is going to be opening T to 0, and I am going to define a voltage V of T. Let's actually call it Vc of T right now. So that's the voltage drop across my capacitor. It also happens to be the voltage drop across my resistor because those two elements are in parallel. And then I'm going to have some current IC of T flowing down through my capacitor and some current R of T flowing down through my resistor. Okay. So for all time less than 0 minus, our circuit is at DC steady state. Which means it would look something like this. Here's our source voltage. Our switch is closed. So our voltage source is directly connected to our resistor. Because we're at DC steady state, our capacitor looks like an open circuit. Here we have our capacitor voltage, Vc of T. Here is our capacitor current, IC of T. Here is our resistor current, IR of T. And by inspection, we can easily see that Vc for all time less than 0 minus is simply Vs. Since the voltage drop across the capacitor is non-zero, this means that the capacitor has some amount of stored energy, where the energy stored by a capacitor is given by 1/2 C V squared. Okay. Now for T greater than 0 plus, our circuit is now in a transient condition because there has been a change in the circuit when the switch changes positions. And so what we're going to see is that our voltage source, Vs, is now disconnected from our resistor and our capacitor. And our capacitor is going to gradually transfer all of its stored energy to the resistor, which will then convert that energy into heat. So it extraordinarily similar to what we saw with our inductor from last Thursday. Okay. After a very, very long time, all of the energy that used to be stored by the capacitor will be converted to heat, and the total energy in the system will then be zero, which means that the capacitor current, or excuse me, the capacitor voltage after a very long amount of time falls to zero, just like we saw with the inductor current. So the situation I am describing looks something like this from the perspective of the capacitor voltage. Here's VC as a function of time. Here's time. Let's call this value Vs, and let's call this value of time infinity. Okay. So for all points in time prior to the switch changing state, our capacitor voltage is constant. We are at a DC steady state condition. A very long time after our transient has died out, our capacitor voltage has dropped down to zero because all of the energy that it had stored had been transferred to the resistor and converted to heat. So everything past t is equal to infinity is also DC steady state. And everything in between is our transient condition. And we're going to work out the math for how our capacitor voltage behaves in this area. So we're going to do that by applying Kerchov's current law at the top node. Which will simply give us IR of t plus IC of t is equal to zero. We can express both of these currents in terms of the capacitor voltage VC. So using Ohm's law, this is going to look like 1 over R times VC of t. Our capacitor current is C times the derivative of V with respect to time. This is equal to zero. And once again, we have a linear homogeneous first order differential equation. We are going to assume, just like we did for the case with the inductor and the resistor, that our capacitor voltage VC of t will be of the form AE to the ST. And when we put this guess value in, what we get is 1 over R times AE to the ST plus CS AE to the ST is equal to 0. And I can factor out things. So we'll have a factor of A that's multiplied through by everything. And then we're going to have 1 over R plus SC times E to the ST is equal to 0, where this bit right here that I've underlined is our characteristic polynomial. So if we can make that characteristic polynomial 0, then our equation is valid. And this is true when S is equal to negative 1 over RC. Just double checking my mental algebra here to make sure I did that correctly. Yeah. All right. So I'm going to finish this up on this page. We now know that VC of t is A e to the negative t divided by RC volts. To figure out what A is, we evaluate our expression when t is equal to 0. Right? So VC of 0 is A e to the negative 0 over RC, where e to the 0 goes to 1. From this, VC of 0 is A, and therefore VC of t looks like VC of 0 e to the negative t over RC, which is effectively the same basic thing we got for our inductor circuits. Okay. We have an exponential decay. And the rate of the exponential decay is determined by the values of the circuit elements R and C. Okay. All right, so now let's tie some things together. We're going to talk about the concept of a time constant. So for RL circuits, what we found was that Y of t, where Y here represents a voltage drop across a resistor or inductor, or a current flowing through a resistor or inductor, and it was of the form Y at 0 minus, less than 0 minus, and Y at 0 plus, e to the negative R over L times t greater than or equal to 0 plus. Or an RC circuit, we have just derived the relationship that effectively says Y of t, where in this case Y is either the voltage drop across a resistor or capacitor, or the current flowing through a resistor or capacitor, will be of the form Y at 0 minus, the t less than 0 minus, and Y of 0 plus, e to the negative t divided by RC for t greater than or equal to 0 plus. These expressions are effectively the exact same thing. Okay? The only thing that changes is that little bit acting on inside the exponential function that's acting on time, or the description of the rate of decay. Okay, so electrical engineers don't really care whether or not we have an RL circuit or an RC circuit. We care more so about that rate of decay, and we gave it a special name. called a time constant. So tau is our time constant, and it is the amount of time it takes for a signal to decay to y of 0 plus times e to the minus 1, okay? Which comes out to be how long it takes to decay down to roughly 37%, okay? So if we made a plot here's time, and up here, this is going to be the ratio of y of t divided by y of 0 plus. At t is equal to 0, this is going to have a value of 1. As time progresses, we're going to have our exponential decay like so. And at exactly 1 time constant, the value of this ratio is e to the minus 1. Which is 36.8%. At exactly 2 time constants, we'll have a value of e to the minus 2, which is 13.5% of the initial value. Come here, we'll have 3 time constants. Running out of room here. This comes out to be 5%. And finally, way out here, at 5 tau, this would correspond to a value of e to the minus 5, which is 0.7%. 5 tau is effectively infinity for engineers. So after 5 time constants, our signal, whatever it is, whether it's a voltage signal or a current signal, has decayed to less than 1% of its original value. And so we treat this as a capacitor or inductor effectively fully discharging, okay? So after 5 time constants, our transient condition is effectively over, and we've moved along back to a DC steady state condition, okay? Well, for an RL circuit, tau is simply L over R. And for an RC circuit, tau is simply R times C. So let's talk about how we use the time constant in our analysis. Okay. Step number one, if you'll recall, was to analyze our circuit at t is equal to 0 minus. Step number two was to analyze our circuit at t is equal to 0 plus. And for the examples that we worked on Thursday, step number three was to determine LEQ and REQ during the transient condition. This was for RL circuits. As you can probably surmise, step number three for an RC circuit would be to determine CEQ and REQ during the transient condition. What we're going to do is effectively lump these two things together by saying now we will just determine tau. During our transient condition. Because inherently, in determining our time constant tau, we're going to have to know either LEQ and REQ for RL circuits or CEQ and REQ for RC circuits. Okay, so our step three is now this guy. And our step number four will be plug values into our generic equation, where our generic equation will be y of t is equal to y of 0 minus, t less than 0 minus, and it will be y of 0 plus times e to the negative t over tau for t greater than or equal to 0 plus. So this is our updated methodology. Okay, we're about to make another update to it, but to illustrate why it's necessary, I want to look at a problem. So we're now going to talk about what's called the total response of first order circuits. So can I go? Yes, absolutely, Sydney. let me know when you're ready to move along, please. All righty. So our total response, y total as a function of time, is made up of two parts. The natural response and the forced response. The natural response is what we've been talking about. This is our transient response. When no independent sources are present. So effectively, our natural response is composed of what happens when we take sources out of the circuit, which is exactly what our switches have been doing up to this point. The forced response is what happens when independent sources are left in the circuit, okay? So what I mean by that specifically is with an example of an RC circuit here. Let's say that we have a voltage source RS connected to a switch which is in turn connected to some resistor and some capacitor. Like so. This is our capacitor voltage, VC of t. This is our capacitor current, IC of t. This is our resistor current, IR of t. And we have a switch, but now let's say it closes at t is equal to 0. And we're going to talk about what happens here. Okay. So for t less than 0, during our DC steady state condition, our circuit looks like this. Here's our voltage VC at 0 minus, our current IC at 0 minus, our other current IR at 0 minus. So in this particular case, we can see by inspection that VC at 0 minus is equal to 0 volts. for 0 plus is less than t is less than infinity. So this is during our transient condition. We have our voltage source that's connected to our resistor and our capacitor. Plus minus VC of t, IC of t, and IR of t. So what should we expect to happen? Not mathematically, but qualitatively. If we were trying to describe what's going on here, as time progresses, we should expect that the capacitor voltage is going to start at 0 volts, because that's what the capacitor voltage was at t is equal to 0 minus. And it has to continue being 0 volts at t is equal to 0 plus. And then as time progresses, our capacitor is going to slowly charge up. And it's going to be fully charged when VC of t is exactly equal to Vs. Well, after it becomes fully charged, our transient condition is over. And we'll have this third period for t greater than infinity after our charging stops, where our voltage source is connected to our resistor. Our capacitor looks like it's DC steady state equivalent again, because we're in DC steady state conditions after our capacitor has stopped charging. So here we'll have VC at infinity. This will be IC at infinity. And this is IR at infinity. And we can see by inspection here that VC at infinity is equal to Vs. This bit right here is our forced response. We call it a forced response because our voltage source is forcing the capacitor voltage, in this case, to settle to some non-zero value as time increases. Okay. So what we are going to do is now look at our generic equation and try to include the effects of the forced response, right? So to reiterate, our total response, Y total, is simply our natural response, which is what we've dealt with prior to this point, plus our forced response. So that's going to look like Y at 0 minus, T less than 0 minus. And what I'm about to write down here is intentionally incorrect. So I would appreciate you not writing it, because you're just going to have to erase it in a minute. But I want to explain why it isn't correct and what we have to do to fix it, okay? So our natural response from our prior experience is going to look something like Y at 0 plus, E to the minus t over tau. And then we're going to add to that our forced response, which is y at infinity. Now, the problem with this is that for capacitors and inductors, so specifically capacitor voltage and inductor current, the way that this equation is written does not force those quantities to be continuous functions. So what I mean by that is we know that for IL of t and VC of t, IL at 0 minus has to equal IL at 0 plus, and VC of 0 minus has to equal VC at 0 plus, because the current through an inductor cannot change abruptly, and the voltage drop across a capacitor cannot change abruptly. Well, if we evaluate the expression that I've written up here for our total response at 0 minus, what we'll find is that IL at 0 minus will be equal to IL at 0 plus IL at infinity. And let me just be really clear, e to the minus 0 over tau plus IL at infinity. And we would get a very similar result for our capacitor voltage, which this is only true if our forcing function is 0, the case that we've been dealing with. So how we're going to adapt this is that our coefficient in front of our exponential function, this guy right here, is no longer going to be just IL or y at 0 plus. Instead, what we're going to have is y at 0 plus minus y at infinity. If we change this expression, it forces our function to be continuous as this goes to 1. Okay. So this right here is our new generic expression. Now I want to explain something here, because a question that I get asked literally every quarter is, how do I know whether or not to use this expression, which includes a forced response portion, or whether to use the generic expression that we developed earlier, which does not include this y at infinity stuff. So there is a real reason to use one versus the other, okay? If any independent sources are included in the circuit, so effectively connected to our inductor or capacitor, we should be using the forced response equation, this one that I've boxed right here. If all of the independent sources are disconnected from our energy storage element during the transient condition, we don't need to do the forced response component, because everything is going to settle to 0. Now, if you have trouble identifying whether or not the independent sources are connected or are disconnected, you can just use this expression right here And the only thing that's going to do is you're going to do a little extra work proving that things are settling to 0 at t is equal to infinity. All the other steps are just the same, okay? So let's work an example. Let's say that we have a 10-volt source connected to a 1 kilo ohm resistor. So another 1 kilo ohm resistor, like so. Over here, we are going to have a 10 nanofarad capacitor. And then down this branch, we have a 3 kilo ohm resistor. And we are also going to have a switch. And let's say that this switch opens at t is equal to 0. Our first step will be to analyze the circuit at t is equal to 0 minus. The exact same first step we've taken for all of these circuits. Okay. So at t is equal to 0 minus, our circuit is at DC steady state, which means our capacitor looks like an open circuit. At t is equal to 0 minus, our switch is also closed. So what we're going to have is this. Here's our 10-volt source. Here's our 1 kilo ohm resistor connected to the the other 1 kilo ohm resistor. Here's the open circuit that's representing our capacitor. Oh, and give me just a moment here. Got slightly ahead of myself. The quantity that we are interested in is this current I of t. So here is our current I at 0 minus, and we're not specifically asked for it, but we are going to need to keep track of it. This is our capacitor voltage, DC, at 0 minus. So I'd like some help, if at all possible, determining what these quantities are. Does anybody have any thoughts? So Devarier has suggested that the current at 0 minus is equal to 0. I disagree. So let me explain why. I'll do this simply. So let's assume here that the 10-volt source is supplying some amount of current. It's going to flow through the 1 kilo ohm resistor, and then it's going to see this node in the top middle. We know that none of it can branch off and flow through the 1 kilo ohm resistor to the right, because that 1 kilo ohm resistor on the right is not part of a closed current carrying loop, which means all of that current will turn down. Now the current sees this node in the middle, and it has a choice. It can flow through the short circuit to the left, or it can flow through the 3 kilo ohm resistor. Obviously, it will flow through the short circuit. And then return to the negative polarity terminal of the 10-volt source. So I would argue, based on our qualitative analysis here, that I of 0 minus is 10 volts over 1 kilo ohm, looks like 10 milliamps of current. Does anybody have a problem with the analysis that I've done there? All right, nobody's saying that they have a problem with it, so I'm going to assume that you're all in agreement. Does anybody have any thoughts about the capacitor voltage VC at 0 minus? All right, nobody's volunteering anything, so let's talk our way through it. So what's the voltage drop over the 3 kilo ohm resistor? Anybody have any thoughts about that? Devarier, unfortunately, once again, I disagree. The voltage drop over the 3 kilo ohm resistor has to be 0 volts because the 3 kilo ohm resistor is in parallel with a short circuit, right? So the voltage drop across a short circuit is always 0 volts. And so the voltage drop across anything in parallel with a short circuit must also be 0 volts. Another way that we could think about this is that we know that our 10 milliamps of current bypass the 3 kilo ohm resistor, so that there's no current flowing through the 3 kilo ohm resistor. And then Ohm's law tells us that 0 amps times 3 kilo ohms gives us a voltage of 0 volts. What is the voltage drop across the 1 kilo ohm resistor to the right? Sydney, it's a good question. We can't essentially take out the short circuit. We can essentially take out the 3 kilo ohm resistor. The 3 kilo ohm resistor in this particular circuit isn't actually doing anything. There is no current flowing through it because the short circuit is in parallel with it. There is no voltage drop over it. So we could erase the 3 kilo ohm resistor and lose no information whatsoever about the circuit. Does that make sense? All right. So back to my prior question, what is the voltage drop over the 1 kilo ohm resistor with the polarities that I've indicated in green? So what's the current through the 1 kilo ohm resistor on the right? 0. So since the current flowing through the 1 kilo ohm resistor is 0, the voltage drop across the 1 kilo ohm resistor must also be 0. So if I write a Kirchhoff's voltage law loop, or Kirchhoff's voltage law equation around this loop, what I'll find is that 0 plus 0 plus VC is equal to 0, which means VC at 0 minus has to be equal to 0 volts. Are there any other questions or comments regarding our analysis here at t is equal to 0 minus? All right, so let's move along. Could we have said VC is equal to 0 because of the open circuit? Unfortunately, no, Devarier. So the voltage drop across a short circuit is always 0. For an open circuit, we know that the current flowing through it is always 0. The voltage could be anything. In this particular case, our open circuit voltage came out to be 0 because of that Kirchhoff's voltage law loop equation, where the voltage drops around that closed loop turned out to be 0. Okay, so short circuits have a voltage drop of 0. Open circuits have a current of 0. Always, always, always. Why doesn't I go through this? By the second 1 kilo ohm resistor, you mean the one on the right, Sydney? So the 1 kilo ohm resistor on the right isn't part of a closed current carrying loop because of the open circuit right here. Right? Our capacitor behaves like an open circuit during DC steady state conditions. That was the first relationship we got by looking at the IC is equal to C dV by dt relationship when we talked about capacitors. I want to say this past, last Tuesday, I think. So if the resistor or anything is connected to an open circuit, then we know that current can't be flowing through it. All right. Glad you guys are engaged in asking questions today. It makes me feel like I'm not wasting my time and your time. So thank you all. All right. Our second step also remains unchanged. We're going to analyze the circuit at t is equal to 0 plus. So at t is equal to 0 plus, we are no longer at a DC steady state condition. So we will not replace our capacitor with an open circuit. Instead, and we haven't done this before, we've only dealt with inductors. So for a circuit with an inductor in it, we replaced our inductor with a current source having the same direction and magnitude as IL at 0 minus. For a capacitor, we're going to replace it with a voltage source having the same polarity and the same magnitude as the capacitor had at 0 minus. Our switch is now open circuited, by the way. So what we're going to have is this. Here is our 10-volt source. Here is our 1 kilo ohm resistor on the left. Here is our 3 kilo ohm resistor. Here's the open circuit where the switch was. Here is our right 1 kilo ohm resistor. And then this voltage source is representing our capacitor, and then I'm going to do something to it in just a moment, okay? So the polarity that I've indicated is the same polarity as VC had at 0 minus. Because we have a 0 volt, so let me write this down here. VC at 0 minus must be equal, or excuse me, VC at 0 plus must be equal to VC at 0 minus, which in this case is 0 volts. A 0 volt voltage source is a short circuit, right? Because we want a fixed amount of no voltage drop across it while any amount of current can flow through it. So if VC were anything other than 0 volts, we'd be putting in a voltage source, but because VC is 0 volts, I'm replacing it with this short circuit. Here is VC of 0 plus. Here is I of 0 plus. So, does anybody have any thoughts on how we might analyze this circuit to find I at 0 plus? So a couple of different ways are popping to the front of my thought process. But I think probably the easiest and most straightforward way to do it would actually be to use mesh analysis, okay? So let's call this mesh current IA, and this mesh current IB. We don't have any dependent sources, so we don't have to write any controlling variable relationships. We also don't have any current sources, so we don't have to write any current relationships, so we can just jump straight ahead to our KVL expressions. So KVL at mesh A gives us negative 10 volts plus 1 kilo ohm times IA plus 3 kilo ohms times IA minus IB is equal to 0. KVL at mesh B gives us 3 kilo ohms times IB minus IA plus 1 kilo ohm times IB is equal to 0. And I'm going to solve these two equations simultaneously for IA and IB. All right, so for my first equation, my coefficient for IA is 1 kilo ohm plus 3 kilo ohms, so that's going to look like 4,000. My coefficient for IB is negative 3 kilo ohms, so that's negative 3,000. And my constant term is positive 10 when I move it to the right-hand side of the equal sign. For my second equation, my coefficient for IA is negative 3,000. My coefficient for IB is positive 4,000, and my constant term is 0. And when I solve, I get IA is 1 over 175 amps, which is the same as 5.714 milliamps. And I get IB to be 3 over 700 amps, which is the same as 4.286 milliamps. I at 0 plus is simply IA minus IB, which I get to be 1.429 milliamps. All right, does anybody have any questions or comments regarding our analysis at t is equal to 0 plus? All right, so we're going to have a new step now. Okay. Our new step 3 will be to analyze our circuit at t is equal to infinity. And to be clear, this is a DC steady state condition, right? So t is equal to infinity represents the point at which our transient condition has ended and we've resumed being at DC steady state. I think I've got enough room here. Let's see if we can make it happen. Here's our 10-volt source. Here's our 1 kilo ohm resistor. Here's our 3 kilo ohm resistor and our open circuited switch. Here's our 1 kilo ohm resistor. And because we're at DC steady state, our capacitor looks like an open circuit. Here's VC at infinity. Here's I at infinity. Does anybody have any suggestions about how we could solve for either of those two quantities? All right, so what I'm going to do here is effectively very similar to what we did at t is equal to 0 minus. I'm going to start by looking at my current. So assuming that some current is leaving the 10-volt source, all of it has to flow up, and then all of it has to flow through the 1 kilo ohm resistor. It sees this node, so it has that path down or the path to the right through the open circuit. Current can't flow through the open circuit, so it has to flow down. Now it sees the path down through the 3 kilo ohm resistor or the path to the left through an open circuit. So all of it is going to flow down through the 3 kilo ohm resistor, and it's going to return to the 10-volt source like so. So from this, I would argue that I at infinity is simply 10 volts over 1 kilo ohm plus 3 kilo ohms, which should come out to be 2.5 milliamps. Does anybody have any problem with that analysis? All right, so to determine VC, I'm going to do effectively the exact same thing I did at t is equal to 0 minus as well. Okay, so I know that 2.5 milliamps of current flows through the 3 kilo ohm resistor, which means that the voltage drop across the 3 kilo ohm resistor is 2.5 milliamps times 3 kilo ohms, or 7.5 volts. Since no current is flowing through the 1 kilo ohm resistor on the right, the voltage drop across that 1 kilo ohm resistor has to be 0 volts. And writing a KVL equation around this loop tells me that VC at infinity is 7.5 volts. Any questions or comments regarding the analysis we've done here at t is equal to infinity? All right, so let's move along to step number 4. Determine tau during transient condition. So this is going to entail finding CEQ and finding REQ. I am of the opinion that CEQ will be 10 nanofarads because it's the only capacitor in the circuit. So I feel pretty strongly that I'm not going to get much argument about that one, assuming I wrote that number down correctly, which I better just make sure just for the sake of argument. Yep, 10 nanofarads. All right. So now we're going to find REQ. So this is the Thevenin equivalent resistance as seen by the capacitor. Okay. So we need to be looking at a dead network, which means our voltage source is turned off. Here's our 1 kilo ohm resistor. Here's our 3 kilo ohm resistor. since we're looking at it during the transient condition, our switch needs to be open. Here's our 1 kilo ohm resistor. Here's our open circuit where our capacitor was, and we're looking in through the capacitor terminals. To me, this looks like a 1 kilo ohm resistor in series with the parallel combination of a 3 kilo ohm resistor in parallel with a 1 kilo ohm resistor. So 3 in parallel with 1 looks like 3/4 of a kilo ohm, or in total 1.75 kilo ohms. Does anybody have any problem with how I found REQ, or any questions about why I did what I did to find REQ? All right. So from here, tau is simply REQ times CEQ. So that's 1.75 times 10 to the 3 multiplied by 10 times 10 to the minus 9, which comes out to be 1. Oh, the stylus stopped writing. 1.75 times 10 to the minus 5 seconds. And this will make sense in a moment, 1 over tau comes out to be 57,142.857 per second. All right, so now we're at step number 5. Stuff in. Our generic equation has become y at 0 minus, t less than 0 minus, and it is y at 0 plus minus y at infinity, e to the minus t over tau plus y at infinity for t greater than or equal to 0 plus. So for the current that we're interested in finding, we will have I of t is equal to 10 milliamps, t less than 0 minus. Y at 0 plus was 1.429 milliamps minus y at infinity, where we found y at infinity to be 2.5 milliamps. So this is going to look like negative 1.071 e to the minus 57,142.857 t plus 2.5 milliamps. Where, to be clear, this bit right here represents y at 0 plus minus y at infinity. And this bit right here comes from 1 over tau. All right, so I believe that that's enough out of me for today because I've talked for the better part of 75 minutes straight. We've really covered everything that I would like to cover regarding transient analysis, okay? So what I would like to do with tomorrow's class is to spend the first hour or so just working another, let's say, 2 example problems on this material. And then I'd like to use the second half of the class as a review session for your upcoming exam on Thursday. I will also try to be on Zoom during class time on Thursday for a review session if anybody has any questions they wish to ask, but I don't have anything planned whatsoever for Thursday. So if nobody shows up and asks questions, I will probably log off of Zoom shortly. Okay. So to recap, I'm done talking about transient analysis, which means we finished all of the material for our upcoming exam on Friday. Tomorrow's class meeting will be spent working a few more example problems on transient analysis stuff, and will also serve as a review session. And then Thursday's class meeting can be used for review as well. If you guys have questions, ask me. Devarie, wonderful question. Yes, I am still going to do the 4 different test options. It will be effectively exactly the same as the last exam. So there will be a Thursday afternoon test, a Thursday evening test, a Friday afternoon, Friday evening, Saturday afternoon, Saturday evening, Sunday afternoon, Sunday evening, and you are able to take any of those 8 different options that best suits your schedule. They're all of equal difficulty because they're all roughly the same questions, just a couple of numbers change and things like that. So yeah, you pick whichever one works best with your schedule and go nuts.